You have probably heard of the phrase that spacetime is warped in the presence of heavy objects. In fact, if there is only one thing most people might know about the theory of general relativity, it's that the universe we inhabit is not flat and static, as it might seem at first, but rather curved and expanding. But what does it actually mean for spacetime to be curved? Does it mean that if we travel long enough in one direction, that we eventually end up where we started? Or that the universe is not flat like a plane, but rather bent like the surface of a cylinder, a cone, a sphere, or perhaps even a donut? Well, actually it's none of these. In fact, it's more elegant than that. And to understand why, we first need to understand what it fundamentally means for space to be curved, and then apply this concept to our four-dimensional spacetime. Now this is a tricky subject, so we will start off with a very intuitive and visual approach, and then translate this notion to the language of mathematics. We will end off with a simple thought experiment which definitively shows that spacetime is indeed curved. We start with the visual approach to the fundamental notion of curvature. Flat space is what we're all familiar with. It's exactly that, flat, and not difficult to imagine. All of geometry that we know and love takes place in flat space. We know geometrical facts to be true because we can simply verify them by drawing figures on a flat piece of paper. For instance, if we sum the inner angles of a triangle, they will always add up to 180 degrees, no matter what type of triangle. There are no secrets here. Now we fold our plane, such that two sides touch each other. In doing so, we've obtained a cylindrical surface, which is obviously curved. Note that this folding procedure did not create or remove any pieces of our original plane, nor did we tear the fabric. You can perfectly do this with a sheet of paper without any cutting. And because of this, our geometrical truths, such as the sum of the angles of a triangle, remain valid. Before we continue, let's appreciate the fact that by folding our plane, we went from 2 dimensions to 3, even though the surface of a cylinder is still 2-dimensional. To observe its curvature, however, we need a 3rd dimension to curve into. This is a subtle fact that will be important later on. Let's now turn to a thought experiment to experience how curvature can defy our intuition. Say you're on the surface of a sphere, not much unlike the Earth's surface. You start walking north over a distance r. Then you take a 90-degree turn to your left and continue walking. And then once you've covered exactly the same distance r again, you take a 2nd turn directly to your left. At this point, something peculiar occurs. After going exactly the same distance r again, we arrive precisely at the point where we've started. After some thought, this seems quite off, since if you draw your trajectory on a piece of paper, you see that taking 2 left turns of 90 degrees does not bring you to your initial position. It's not even a closed trajectory. The explanation, of course, is that we've not been traveling on a sheet of flat paper, but instead on the curved surface of a sphere. If we zoom out enough, we see that we have indeed only took 2 90-degree left turns, but that the whole trajectory turns out to be triangular, and this is only true for the surface of a sphere. It is a feature of its curvature, which apparently allows for triangles with 3 90-degree angles. Just to be sure that we're dealing with something peculiar here, let's now travel over the same trajectory, but in different spaces. On a flat plane, when we make 2 90-degree angles, we evidently do not end up at the same point. However, even on the surface of a cylinder, which we intuitively know to be curved, 2 90-degree angles do not result in this triangular trajectory. This gives us a first hint of the existence of different types of curvature. Even though we consider both a spherical and cylindrical surface to be curved, they are in fact fundamentally different. Visually, the difference comes down to being able to determine whether the surface is curved or not without having to zoom out. And let me explain this by taking the triangle as an example. On the spherical surface, we drew a triangle with 3 90-degree angles. And since the sum of the angles is larger than 180 degrees, we can conclude that we are dealing with a curved surface. And there is in fact no need to zoom out in a third dimension to verify this. In the case of the cylinder, on the other hand, 3 90-degree angles will never make a triangle. In fact, any triangle you draw on its surface will have a sum of angles of exactly 180 degrees. This is indistinguishable from drawing on a flat plane. The only way for you to deduce that the surface is curved is to zoom out in an extra dimension. Because in this case the curvature is only observable from another dimension, this type of curvature is called extrinsic. You can think of it as a flat plane in disguise, folded in an extra dimension. The sphere's curvature, in contrast, can be observed without leaving its surface. Just draw a triangle and measure the sum of its angles. This is called intrinsic curvature. Let's take a step back and see how this applies to our universe. It turns out that our spacetime is intrinsically curved, like a sphere is. As a consequence, our universe does not require an extra dimension to be curved into. Saying that spacetime is curved does not imply the presence of another dimension in which it is embedded, or in which it floats, to say it more vividly. Therefore, even though the universe is expanding, it does not need anything to expand into. Now that we have an intuitive and visual understanding of curvature, let us translate these concepts into the language of mathematics and pin down the difference between the two types of curvature. And to make this transition as smooth as possible, we look at another visual characteristic of intrinsically curved surfaces. We do this by introducing parallel transport. It's a procedure where we move a vector along a closed trajectory while keeping it parallel to itself at each step along the way. On a flat surface, this procedure is pretty straightforward. The ingredients are a closed trajectory, which in this case is a triangle, and a vector pointing in some initial direction. While we guide the vector's origin around the loop, it remains parallel to itself, pointing in the same direction along the way. Once we've returned to our initial position, we see that it overlaps perfectly with how it started, still pointing in the same initial direction. What about the surface of a cylinder, which we know is extrinsically curved? Again, we define a closed trajectory on its surface and start out with our initial vector that we're going to transport around the loop. In this case, you probably notice that the vector seems to change the direction in which it points. However, this is still parallel transport. If we would zoom in a lot and make the arrow very short, such that it does not stick out as much, it indeed points in the same direction at every step along the way. After completing the full trajectory, we see that the vector overlaps perfectly with how it started off, exactly as was the case for the simple plane. And this similarity again shows that extrinsically curved spaces are basically flat spaces in disguise. Speaking of curved surfaces, you can probably see where this is going. If we now turn to our intrinsically curved sphere, things will be different. The trajectory will be triangular, in fact the same triangle we had before, the one with the 3 90-degree angles. As we start moving the vector over the curved trajectory, while carefully making sure it is kept parallel to itself at each step along the way, we see something interesting unfold. We observe that once it returns to its initial position, it will in fact not overlap with the initial vector. It now points in a manifestly different direction, a hallmark of intrinsic curvature. We can intuitively imagine that the difference in direction between initial and final vector serves as a measure of how intrinsically curved the surface actually is. And this is exactly how we will quantify curvature later on. At this point, we have all of the intuitive and visual tools to cast these findings into a mathematical formulation. However, if you don't feel up to it, feel free to skip ahead to the practical real-life experiment and see how we utilize these concepts to unambiguously show that the spacetime we live in is indeed intrinsically curved. To start our mathematical formulation, consider the flat plane with our trusty Cartesian coordinate axes x and y. In this plane we have 2 points labeled A and B, and what will be central to our understanding of curvature is the distance between these 2 points, which we call delta s. The key question then will be to express this distance in terms of the chosen coordinates, in this case the Cartesian coordinates x and y. If we define the difference in x and y as delta x and delta y, then we can use the Pythagorean theorem with delta s at its hypotenuse to achieve our goal. We get delta s squared is delta x squared plus delta y squared. Without altering the underlying flat space, which is our plane, we can of course decide to choose a different set of coordinate axes. Let's take for instance polar coordinates. Here we have a radial coordinate r, being the distance from the origin, and the angular coordinate theta, indicating the angle with the horizontal direction. Our objective remains the same: express the distance delta s, which is unaltered, in terms of the new coordinates. Now, however, it becomes somewhat unclear how to express this delta s as a difference in the polar directions. Instead of delta x and delta y, we now have delta r, the difference in distance from the origin, and delta theta, the difference in angle between both points. Now, without going into the details, it turns out that for polar coordinates we can write the following: delta s squared is equal to delta r squared plus r squared times delta theta squared. This formula is very similar to the one we had in Cartesian coordinates. One notable difference, however, is this r squared in front of delta theta. Therefore, the difference between 2 points, as expressed as a difference in coordinates, also depends on how far away from the origin your 2 points are. Roughly, this can be understood by the following. Consider the distance between 2 points at the same distance from the origin, so delta r being 0. We see that when moving both points away from the origin, while keeping the difference in r and the difference in theta unaltered, the difference between these 2 points nonetheless increases. The r squared in the formula takes care of this phenomenon, and thus the formula for distance in polar coordinates becomes dependent on the absolute value of the coordinate r. Thus, we can describe the same distance in flat space between points A and B in 2 different coordinate systems. This results in 2 different formulas for the same distance, each valid in its own coordinate system. To generalize the way we calculate distances to other coordinate systems, or more importantly to curved spaces, we introduce the central player in our story, the metric. This key object is basically the ultimate measuring tool in geometric spaces. In essence, it tells us how to measure distances and angles for a given coordinate system. You can basically think of it as the abstract concept of the set square we use in school. Starting with the basics, you already know the metric for Cartesian coordinates. It's simply the distance between 2 points in the Cartesian system. For the metric, however, we consider infinitesimal distances. Notationally, this simply means replacing the delta with a small d. Then it's this ds squared that is called the metric. However, there is a more common and more tangible way of representing it, namely its matrix form. This is what it looks like for our case and how to get from one notation to the other. On the rows and columns, there are the infinitesimal distances in the direction of the coordinates, in this case dx and dy. The elements in the matrix are then the coefficients from our formula when we multiply these small distances. In this case, we have dx squared and dy squared, and therefore the corresponding matrix elements are simply 1. And because in this case the matrix only contains constant numbers, we call it coordinate independent, which is an important fact for later on. And these are basically all of the ingredients you need to understand the metric, which is the key building block to describe curvature. In fact, we can now construct the metric for different coordinate systems, and without going into the details, you can roughly understand what it means. For instance, revisiting now the same flat space, but now with polar coordinates, the infinitesimal differences in each direction change. Instead of dx and dy, we have dr and d theta. And as a consequence, the metric formula also changes to the infinitesimal version we found before. This in turn alters the metric matrix, where now the r squared appears on the corresponding place. And this time, the matrix does contain a coordinate of the system, namely this r squared, and thus we call it coordinate dependent. Up to this point, we only considered flat space. We used the metric to describe the distance between 2 points, but with two distinct rulers, the coordinate independent Cartesian metric and the coordinate dependent polar metric. Of course, things get much more interesting once we turn to measuring distances in curved spaces. Here, the distance between 2 points will not always be a straight line. The metric, being our universal measuring tool, will take on this role of curved ruler, and it will do so in a predictable way. So let's consider the usual suspects. First, the extrinsically curved surface of a cylinder, where there is not much of a difference with polar coordinates. We know that the coordinates change. In this case, dr changes to dz, which is a change along the height axis. Thus, the formula for distance ds changes, which in turn alters the numbers in the metric matrix. And note that this capital R here is the radius of our cylinder and thus a constant. Therefore, the metric for a cylindrical surface is coordinate independent. And for the sphere, we can do exactly the same procedure. First, the coordinates change to spherical coordinates, but with a fixed r, because a point is determined by the two spherical angles. Therefore, the formula for distance changes, and this time more substantially so, and as a consequence, the metric matrix changes according to the formula. And note here that the matrix contains a theta, and therefore it is coordinate dependent. Now that we understand that the metric describes how to measure distances in different coordinate systems, we want to tie this back to curvature. In particular, what the metric can actually tell us about the curvature of the underlying space. At first sight, we don't seem to get very far. For any space, we can choose an arbitrary coordinate system to describe it. And therefore, the corresponding metric seems to be an arbitrary choice as well, not something inherently to the underlying space. For instance, we describe the flat plane by a coordinate independent metric in Cartesian coordinates, but a coordinate dependent metric in polar coordinates. However, the metric's value as an indicator for curvature is salvaged by the fact that not every coordinate system can be fit on any space. Some combinations simply don't work. This is the mathematical way of saying that you cannot perfectly cover a ball with a sheet of flat paper. In mathematical terms, a sphere cannot be described in Cartesian coordinates. To make progress, we use this information together with the fact that some metrics are coordinate dependent, such as polar coordinates or spherical coordinates. And we get the following. If we are able to write the metric in a form that does not depend on the coordinates itself, so being coordinate independent, then the underlying space will definitely be flat. Of course, we can flip this logical statement around, saying that if the underlying space is not flat and thus curved, we will never be able to find a coordinate independent metric. Alright, so we're done, right? We just need to find a coordinate independent metric and we can rule out curvature for the underlying space. Let's look at some examples. For a flat plane, we can indeed find a coordinate system with corresponding metric that does not depend on the coordinates, namely the Cartesian coordinates. Now, I know we can measure distances in polar coordinates, which gives us a metric that does depend on the coordinates, but that does not matter. What matters here is that we have at least one coordinate independent metric. So what about the cylinder? We know the cylindrical surface to be extrinsically curved, or curvature in disguise. How does our rule apply here? Well, we have cylindrical coordinates, which we saw before, which are coordinate independent since r is constant. However, note that we can also define Cartesian coordinates on the cylindrical surface. If we draw parallel horizontal and vertical lines, all of them will intersect at 90-degree angles, exactly what Cartesian coordinates require. Therefore, we have found two coordinate-independent metrics. From this, we again conclude that the cylindrical surface is actually flat, and that the curvature we see is only a consequence of folding it into a third dimension, a prime example of extrinsic curvature. This of course brings us to the surface of a sphere, which we know to be intrinsically curved. We already saw one possible metric to describe distances in this case, and this one is coordinate dependent. Can we thus conclude that this surface is intrinsically curved? Well, not exactly. Here we hit on the limits of what the metric in itself can tell us about the curvature of space. We expect that if we try and look for a coordinate independent metric, we will never find it. However, we can never know for sure whether we did not find it because it doesn't exist or because we simply did not look hard enough, even though it does exist. It's like finding a needle in a haystack without knowing whether it's even there. You cannot draw conclusions about its presence on the basis of not finding it. Therefore, we continue our journey to find some measure that will give us a definitive answer to whether a space is curved or flat. At this point, the mathematics become quite daunting, and I will cover the details in another video for those willing to take on a challenge. Here, we will skim over the details and focus on the different steps involved to get to a final curvature measure. We have established that curvature has something to do with the metric being dependent on the coordinates itself. In practice, this means that the metric, labeled g here, changes depending on where on the surface you are. So g at point A will be different from g at point B. The subscripts mu and nu on g indicate the elements in the corresponding matrix. More generally, all of the indices that follow are placeholders for the underlying coordinates. For instance, in spherical coordinates, theta and phi. Next, we introduce a mathematical object that connects the metric of different points in space to each other. The exact expression is a combination of the metric and its derivatives. Specifically in general relativity, it's called the Levi-Civita connection. And intuitively, it's the mathematical expression that allows us to compare the direction of vectors at different locations on our surface. And this brings us to the final object which definitively describes the curvature of the underlying space, the Riemann tensor. It's a tensor that is defined by taking a combination of connections which themselves include the metric. Therefore, the Riemann tensor is completely determined by the underlying metric. Without going into the details, we can still get some intuitive feeling of how this object embodies curvature. And we will do so by coming full circle, revisiting our intuition of parallel transport. So even though the Riemann tensor looks daunting, we will still give it an intuitive interpretation based on parallel transport. This time, the explicit trajectory and the pointing direction of our vector will be crucially important. First, let's define the directions. The theta direction are the meridians, and the phi direction is parallel to the equator. Now, each index in the Riemann tensor plays its part in parallel transport as follows. First, we pick an initial vector on our surface, and we explicitly point it in a specific direction. Here, it points in the theta direction, and this is precisely the meaning of the first index, sigma. Then we decide on the trajectory to transport the vector. We choose a closed path with two legs in the theta direction and the two other legs in the phi direction, with each leg being a meridian connecting two corners. At this point, we are ready to transport our vector. The first leg of the trip will be in the theta direction, and this is encoded in the mu index. Then we move the vector, always parallel to itself, in the phi direction, which indicates the nu index. At this point, we move back in the negative theta direction, and to get back to our initial position, we again move in the opposite phi direction, 3 of the 4 indices are already accounted for. As we saw earlier, the final and initial vector do not overlap, a hallmark of intrinsic curvature. Now, however, we can quantify this more precisely. The discrepancy in direction between the two vectors can be encapsulated in their difference vector. This vector itself has 2 components, one in the theta direction and one in the phi direction. And it's these 2 components that are exactly what the Riemann tensor represents. The final index, rho, indicates which component of this difference vector we consider. Ultimately, we find that the Riemann tensor represents the components of the difference vector after parallel transporting an initial vector over a well-defined trajectory. A direct consequence of this interpretation is that if there is no difference in initial and final vector, as was the case for both flat space and extrinsically curved cylinder, the Riemann tensor is 0. We can even put it more stringent. Space is flat if and only if the Riemann tensor is 0. And this leaves us with exactly what we were looking for, namely an unambiguous measure to see whether a space is flat or curved. Now that we have a better understanding of what curvature is, we take a step back and bring this notion to reality and, in particular, apply it to our own universe. In order to demonstrate that spacetime is indeed warped in the presence of matter, we will do a thought experiment. Let's say we're standing on the Earth's surface and have to our disposal a rocket in which we can travel at very large speeds. To check whether spacetime is indeed curved, we are going to travel along 2 paths, and intuitively they should end up at the same point. Both trajectories will consist of 2 legs, one parallel to the Earth's surface and the other perpendicular to it. In the first scenario, we start by taking the perpendicular leg first, flying straight up for exactly 1 hour. After this time, we make a turn and continue flying for 2 more hours, but now parallel to the Earth's surface. And upon arrival, we mark our destination point. In the second scenario, we swap around the perpendicular and parallel legs of the trip. We first travel near the ground and parallel to the surface for 2 hours, and only afterwards we gain altitude by traveling straight up for 1 hour. Again, upon destination, we mark our position. The crux of this experiment is to compare the arrival position of both scenarios and see whether they overlap. Now, you might immediately jump to the conclusion that evidently they will overlap. And of course, you would be right, if space is flat. Because in flat space, those 2 paths should indeed end up at the same point, which can be easily drawn to verify. In curved space, however, such as on the surface of a sphere, such 2 trajectories will not end up in the same point. This is because traveling the same distance west closer to the North Pole will allow you to cross many more lines of longitude than you would at the equator, simply because the closer to the poles, the smaller the distance between the lines of longitude. This gives us a clear distinguishing factor in our experiment. If we travel through flat spacetime, we should end up at the same point for both trajectories. If we don't, we know we've been moving through curved space. To settle the dichotomy, we need to take into account one of the most intriguing features of the theory of general relativity, namely that the closer you are to a massive object, the slower you experience time compared to someone further away. In our particular scenario, this feature is manifested in the following way. Time moves slower for someone near the surface of the Earth compared to someone further away, or to put it more vividly, someone near the surface will age more slowly compared to someone traveling in orbit. Therefore, 2 hours near the surface will take longer compared to 2 hours up in the air. The person on the blue trajectory will experience her clock ticking slower compared to this person further away from the surface on the red trajectory. As a consequence, she will have more time to travel further, and both parallel legs will not be of equal length. Therefore, when both travelers complete their trajectories, based on their own clocks they carry with them, they will not meet at the same point. Now, this of course can never occur if spacetime would be flat, and thus we conclude that the 4-dimensional spacetime we live in is indeed curved.